piecewise smooth surface, its graph is a piecewise smooth surface. Okay? And we're going to play with, such kind of f's, okay, for which you have piecewise smooth surfaces, whose graph is a piecewise smooth surface. Okay? Okay. So now we are moving to what? We are moving towards really a simple set of observations. Okay, and that simple set of observations is going to give me. Let me state, this Gauss Divergence Theorem, and then give you a short proof of it based on these two definitions. So these two definitions are important. So if you have a piecewise smooth surface, you can have piecewise smooth surface in many different ways. But one way is very easy, that you just take a piecewise smooth graph function and look at its graph actually. And its graph is going to be a piecewise smooth surface. But it doesn't mean that that's the only mean to define piecewise smooth surface. You can have other ways to define the piecewise smooth surface as well. For example, the way I told you that, okay, you take, for the bottom you have a parameterization, for the top you have parameterization, and for the cylindrical part you have parameterization, and you put them together, you get a parameterization for the entire surface. Okay. All right. So what's Gauss divergence theorem? It's really analog to what do you have in 3 dimension. Okay. And what was the Gauss divergence theorem in 3 dimension or 2 dimension? So then in 2 dimension you said that you have this region, or maybe you have, for example, in R2 you have a vector field. Okay, so you have vectors everywhere on entire R2. Okay, and on this R2 you are talking about a simple smaller region actually. Okay, that has a boundary, for example, C. Okay, then the Gauss theorem says that if you sum up all divergence that is happening within the region is going to be equal to the flux of the F that is exiting through the boundary actually. Okay, so the flux of F that is exiting the boundary in the normal direction. Okay. So what would be in this case actually, in 3-dimensional case, you're going to have the precisely same situation. So instead of a region, you have, for example, you have a vector field, okay, going all over, and now you're talking about a volume. And you want to say that if you take a hypothetical volume, okay, how much of divergence is going on in that volume? How much of F is diverging out in that volume? What kind of divergence is going on in that volume actually? And when you put them together, okay, when you sum them up all, is going to be equal to, the flux of F that is, for example, happening across, what do you call that, volume actually. But in this case, the volume is going to be surface, not a curve. So that's the key difference actually. That I can have a volume, okay. So when I say that I have this volume, so that this volume comprises of 6 surfaces as a boundaries actually. Okay, so 6 surfaces. So if you want to see that, so what Gauss divergence theorem is telling you, the amount of divergence of F that is happening, vector field that is happening inside this volume is equal to the amount of F that is exiting through all these surfaces actually, which are the boundaries of what you call the volume. So this is what the divergence theorem is. So let me put it precisely. So let F be a vector field. Defined on V or a neighborhood of V. Okay. Define V. But this V is a Gauss region. So shall I define first Gauss region? So what's a Gauss? A Gauss volume actually, a Gauss region, yes. So Gauss region is simple. It's a volume whose boundary is a parametric surface. Simple. So any volume whose boundary is a parametric surface is a Gauss volume. For example, really this mouse, okay, is representing a Gauss what do you call, region, because its boundaries consist of what do you call a parametric surface actually. So it's really a piecewise parametric surface. Piecewise. Okay. So the Gauss region. Okay. So I'm going to say a subset V that is subset of R3 is Gauss region. Okay. If V is Fubini is type 1 and 1, 2 and 3, so it should be both or all three. So I'm not getting into what do you mean by Fubini type 1. So by Fubini type 1 you mean that you have a volume whose top and bottom is a surface actually. Okay, a parametric surface. And the second is that boundary of V is a piecewise parametric surface. Piecewise parametric surface. So see, understanding the theorem is not a big deal. The real thing is understanding the assumptions. What is the framework that we are working on actually? Okay, then that's what is going to make things coherent. So what is Gauss region? So it's a volume in R3 that is Fubini type 1, 2 and 3, and its boundary is a piecewise parametric surface actually. And this theorem is true for such kind of Gauss regions actually. Okay. Fubini, for example, sphere is also a piecewise parametric surface whose boundary is just one piece. Okay, the boundary of sphere. Are you getting the point? So I'm saying that again and again that piecewise parametric surface is a bigger category of surfaces, which includes our all intuitive surfaces. For example, it's going to contain torus and sphere. Okay, but for example, a box, a cube, is not a surface as per our basic definition of surface. Okay, because you have these boundaries which are troublemaking. But parametric surfaces, piecewise parametric surface can include the cube as well. Okay, and all different kind of regions. Okay, so let F be a vector field defined on a Gauss region V. Then I have a simple thing that you see that how much of divergence is happening in this small volume dV, which is dx, dy, dz, and then sum that up all divergence over the entire V. This should be equal to the F that is exiting in the normal direction, okay, through the boundary V. So that's really a surface integral of a scalar field F dot. Okay, so that's what really the divergence theorem is roughly telling you, where n is outward unit normal, outward unit normal onto boundary. Is it making sense? Now think of a cube in your head. So the cube has these 6 surfaces. For example, if you want to apply or you want to compute this on a cube, then boundary of V is not a simple one surface, it's a combination of 6 surfaces. So you need to split this integral into 6 surfaces integrals. And the n would change on each of the integral actually.
Yes.
Are you getting the point? So that is going to equal to the surface integral, volume integral. And you see that it avoids you to this theorem avoids you to calculate the 6 surface integrals. It says you forget about 6 surface integrals. Okay, just compute the divergence and integrate it all over, for example, the cube. Okay. So it's a beautiful, very intuitive kind of a theorem. I would like to write a proof of it. Okay, careful proof. Maybe I'll leave some details for you, but everything is going to be there, so makes sense. So here's a proof. So I know that V is Gauss region, so it must be Fubini type 1 and type 2 and type 3. Okay. Let's see what we get first from when the V is Fubini type 1. So I would like to exploit this fact that V is Fubini's type 1 actually. So if it is Fubini's type 1, okay, and its projection with projection of the shadow of the V in xy plane, projection in xy plane is, let's call it sigma. Okay, let's call it sigma. Okay. So if I have a sphere, its shadow is going to be disk. If I have a cube, its shadow is going to be disk. If I have a cube, shadow is going to be a plane or a finite rectangle, square. And if you have a cylinder, the shadow is going to be disk. Okay. If you have a torus, the shadow is going to be what, you know, a strip actually, a circular ring. Okay. Anyway, so V is the Fubini type 1 with the projection xy plane sigma. Okay. So that's first point. Second point, let's assume that F goes like this. So F is this, what do you say? So F is this PQR actually. Okay. Where P is a function of U and V, Q is a function of U and V, and R is a function of U and V. Okay. U and V. No, that depends on X, Y, Z. Yes. The whole, because it's the vector field defined on the volume V. So P, Q, and R are the all functions of X, Y, Z, like, for example, F, because F is a vector field on R3. It's not, they're not.
Sir?
Yeah.
So here in definition, it is written that if the vector field is smooth. So how a vector field is smooth, sir?
Smooth इस वजह से होगी, so एक मिनट.
PQR is smooth होगा.
Yes. एक मिनट. Does it say smooth?
Yes, sir. Sure.
In the assumption.
Yes, sir. Let F be a smooth.
So I should have the smoothness. Let F be I must write the smoothness. By smooth it's simple. It's each component is smooth.
Each vector.
Yeah. Each vector, each component P, Q, R is a smooth. So P is a map. So these P, Q, R's are the maps from R3 are in fact sigma. R3 into, for example, R, or maybe you can put V into R actually. So they are smooth. Alright, so I'm writing it explicitly. And if it is Fubini type 1, so you're going to have two surfaces making there, for example, top and bottom, what we call boundaries. So let's call these surfaces as, so let's assume that you have this phi 1 and phi 2, okay, that are defined on sigma under the R be piecewise smooth. So they are piecewise smooth. Okay, piecewise smooth. And if they are piecewise smooth, they are going to generate, you know, what do you call two surfaces. So the graph of phi 1 is going to be a piecewise parametric surface, and graph of phi 2 is also going to be a piecewise parametric surface. So let's denote SI to be the graph of piecewise smooth surface I actually. So it's going to be say UV xy phi I of xy. Okay, such that x comma y are from this sigma. Okay? But if you look at it, so what kind of thing you are talking about? For example, you look at the cylinder actually. Okay, you look at it, the cylinder, or look at the cube actually. Okay, look at the cube. Cylinder, cube. So its top is a surface and the bottom is a surface defined on what you call sigma. But there is another surface which is really okay. So if you have a volume between these two surfaces, so naturally there is going to be a third surface which is connecting, all three. For example, if you have a cube, you will have this four sides creating a surface. If you have a cylinder, so the top and bottoms are surfaces, but you're going to have another surface that is creating really the boundary of it actually. Okay? So let's call that surface as S3. Okay? As S3. So what would be the key thing in an S3? The key thing in S3 is going to be that it's a collection of X, Y, Z. So it's a collection of X, Y, Z, for which X, Y's are from sigma. But how about Z? So the Z lies between these two surfaces, the top and bottom surfaces, right? So keep cylinder in your head, for example. So you can say Z is between phi 1 of xy and phi 2 of xy. I'm assuming that you remember the definition of Fubini type 1. So Z is really the all points between phi 1 of xy and phi 2 of xy. So that's your S3. Is it making sense?
Yeah.
And now consider the first, for example, surface. So consider the f dot n, but on boundary of V. Okay.
Yes.
But the f dot n on boundary of V is going to be equal to what? So the boundary comprises of three surfaces. Okay. So which surfaces? S1,
S1, S2, and S2.
F2. Okay. And S3. Here you have it. Can you say something interesting? Okay. Before even getting into it, what would be f dot n? Okay. All right.
So f dot n means, I think, how much vector field is going.
No, वो तो ठीक है. But I'm saying that so instead of calculating f dot n, because what you need to do, you need to take the dot product of p, q, and r with each of, for example, this normal vector and add them up. So I don't want to, for example, consider the entire f at once, but let's consider, for example, r at first actually. It's the first component. So I can put the value of f here, and I can have a p dot. Okay. So here's the thing. So if I have an f here, so I can put pi plus qj plus rk here. Okay, everywhere. So I'm going to have a similar kind of identity for r and q and p actually. Are you getting the point? So I'm saying that let's not consider first entire f, but first consider the first component of last component of it. For example, rk actually, where the k is the unit vector. Are you getting the point? K is a unit vector. So you're going to have rk here.
So मतलब ये vector field change हो रही है.
RK here, yes. So everything is same, and RK here. And think about it. If we can just do this for Rk, the argument for PQR is going to be same actually, precisely. There's nothing special about R, argument for P and Q is going to be same. But for R, I can exploit one thing. And that one thing is that V is Fubini type 1, type 2 and type 3. Okay? Now since here V is Fubini type 1, so this integral over boundary of V can be splitted into this. Now here's a question. Can you say something interesting about, say for example, this third surface? So imagine in your head a cylinder or a cube, something like that, in which you have a top surface and a bottom surface. And this N, so S3 is really like the boundary of it. Okay, a cube. In case of the cube, it's going to be, what do you call these? A combination of 4 planes. Are you getting the point? Parts of the plane. So, what do you think? What should be the relationship between N and K dot actually? K. So K is pointing where?
Perpendicular.
So it should be perpendicular actually. Think about it. So if you have a cylinder or a cube, the N will go this way actually, while the K has this direction. Are you getting the point? So this N is always going to be perpendicular to the K hat actually. So you're going to have this be 0. So this guy is gone. So the only thing that you need to now focus is on the rest of 2 integrals. Okay? All right.
Sir, what about S1 and S2?
So that's what we are dealing now. So I'm saying that for S3, yes, this will go away. Okay? This will go away. Here's another interesting thing. चलो वो मैं बाद में बता दूँ. So let's think for example this first integral S1. S1 की parameterization क्या है? So what is the parameterization of S1? So this is really the parameterization of S1 actually. Okay? But for the parameterization I don't need to take the entire sigma, but I need to take the open subset in it actually, जो के U also. In other words, roughly you just get rid of the boundary of the sigma from this actually. Okay? So here's the thing. So let Pi of UV, where I could be 1 and 2, जब भी मैं I लिखूंगा, I'm going to mean 1 and 2, is going to be what? UV and phi I of UV, okay? Where I is 1 and 2. Yeah, here we can be parameterization. So let's assume that these are the parameterizations of SI, where I is 1 and 2. Okay? Let's assume this. So in order to compute these two integrals, you need to first know the n. That's really the case. Yes. So what would be n actually in this case? N in this case is going to be, so I can compute it, I can take the cross product of it and so on and so forth. So I'm just directly writing it. So the n is going to be this. So it's going to be minus partial phi 1 by u minus, or maybe phi I if I write phi I by u, and minus partial phi I by v and 1. For the graph surface, previously if we had, for example, if we denote this by f, you remember you have here minus fu minus fv and 1 actually. So on the f, instead of f, now you have phi actually. So it really makes sense. Otherwise you can calculate it actually. Are you getting the point? And now in this dot product, I know for one thing for sure. So what is going to be the k dot n in this case actually? Think about it. So n has 3 components, these 3 components. But two components are not going to survive. The only this component is going to survive, and this is going to be really 1. Is it making sense?
Yes.
So this is going to be really 1 actually. For example, for the surface 1, this is going to be, let's call, for S1, let's call this normal vector as N1, and it's going to be 1. And for S2, can you see that there is going to be a 1 difference? What would be that 1 difference actually?
So minus sign.
So it's going to be minus sign. Yes. Can you see it? So that's what the only difference that you're going to have actually in both cases. Okay. And now I can really wrap up the things because we have got almost everything that we want. So this double integral of this RK hat dot n over the boundary of V is going to be equal to that over sigma you integrate what? R and K dot n. So it's going to be, the first is going to be, for example, R of what do you say? Maybe R, but you need to evaluate it at what? X, Y, Z, but the X, Y, Z are what? The points of the surface S1. Okay, surface integral है ना? कैसे compute करते हैं? So you take your parameterization, you substitute into the what do you call vector field, okay, and then take the dot product with that PU cross PV actually, okay, which is known to be 1. So it's going to be, for example, for the first integral, if you have this, so let's call it PUV, P1 UV, okay, and K dot n to ho gaya 1. So let's call this as du dv minus, okay, sum, okay, sigma r of p2 uv and du dv actually. Isn't it? ठीक है? I can rewrite this as minus, if I combine them, put them together, I can have sigma r of P2 UV d minus r of P1 UV and du dv. Agreed? ठीक है? Is it making sense?